The heart weighs 400 pounds. Not the whole animal, just the heart. It's the size of a small car, with chambers large enough that a human could crawl through them. When it beats, it moves 60 gallons of blood through arteries so wide you could swim through the largest ones. The beat itself is so powerful, so slow, that it can be detected by sensors from miles away. 2 beats per minute when the animal is diving. A rhythm so drawn out that each contraction takes longer than most animals' entire heartbeat cycle. This is the cardiovascular system of the blue whale. The largest animal that has ever lived. Larger than any dinosaur. Larger than any creature that has ever existed on Earth in over 500 million years of complex life. An adult blue whale can reach 100 feet in length and weigh over 200 tons. That's 400,000 pounds. The tongue alone weighs as much as an elephant. The skull is so massive that a fully grown human standing inside the mouth would barely reach the roof. A single vertebra from the spine weighs more than your entire body. These numbers seem impossible. They seem like exaggerations, like the kind of measurements that get inflated over time until they bear no resemblance to reality. But they're not. They're documented, measured, verified by scientists who've examined blue whales, weighed their organs, analyzed their biology. And the most remarkable thing isn't that blue whales exist, it's that they exist at all. Because at this scale, biology stops working the way it does for normal animals. Physics creates problems that shouldn't have solutions. And yet the blue whale has solved all of them, using adaptations so extreme they rewrite the rules of what living things can do. So, how did the largest animal ever get this big? What biological innovations allow something weighing 200 tons to function when physics says it should collapse under its own weight? And why has nothing, not the largest dinosaurs, not any creature in Earth's history, ever exceeded the blue whale's size? Because when you understand the answers, when you see exactly what the blue whale had to overcome and how it did it, you realize that this animal represents the absolute upper limit of what biology can achieve. The blue whale isn't just big, it's as big as anything can possibly be. A blue whale is feeding off the coast of California. Its mouth opens and the entire front of its body transforms. The throat, normally sleek and streamlined, expands outward like a balloon inflating. Grooves that run along the underside of the whale, called ventral pleats, unfold and stretch, allowing the throat to balloon to many times its normal size. Water rushes in. Not a little water. Not a few gallons. The whale is taking in up to 10,000 gallons in a single gulp. That's enough water to fill a small swimming pool. The weight of this water alone is over 40 tons, nearly doubling the weight of the whale's head. Then the mouth closes. But the water doesn't just sit there. The whale's tongue, that massive elephant-sized organ, pushes upward and forward, forcing water out through baleen plates that line the upper jaw. These plates are made of keratin, the same material as your fingernails, but arranged in hundreds of thin, flexible sheets that hang down like a curtain, each one fringed with hair like fibers. The water passes through these fringes, but the krill don't. Thousands of tiny shrimp-like creatures, each one maybe 2 inches long, get trapped against the baleen as the water flows out. When all the water is expelled, the whale uses its tongue to scrape the krill off the baleen and swallows them in a single mass. One gulp. Thousands of krill consumed. And the whale does this dozens of times in a feeding session, sometimes hundreds of times in a day. This is how the largest animal ever survives. Not by hunting large prey like every other giant predator in history. Not by eating fish or seals or anything substantial. By filtering tiny crustaceans out of seawater, consuming them in such massive quantities that it adds up to 4 tons of food per day. Think about what this means from an engineering perspective. The whale has to open its mouth wide enough to engulf 10,000 gallons of water. It has to have a throat that can expand to hold that volume without tearing. It has to force that water back out through a filtering system efficient enough to catch prey that's barely bigger than your thumb. And it has to do this while swimming, while maintaining forward momentum, while not sinking from the massive weight of water it just swallowed. Every part of this process requires biological innovations that don't exist in other animals, and understanding them reveals exactly how the blue whale broke through size barriers that limited every other creature in Earth's history. Start with the mouth. When a blue whale opens its jaws, it's not like a lion opening wide to bite. The whale's lower jaw doesn't just hinge downward, it actually unfolds, rotating outward at an angle that would dislocate the jaw of any other mammal. This is possible because the two halves of the lower jaw aren't fused together at the front like in most mammals. Instead, they're connected by flexible tissue that allows them to separate and spread apart, widening the mouth to an opening large enough to engulf that massive volume of water. But the real innovation is in the throat. Those ventral pleats, the grooves that run from the whale's chin all the way back to its navel, are structural genius. They're essentially folded tissue, like an accordion or a paper fan. When the whale needs to expand its throat, these pleats unfold, and the tissue between them stretches. The pleats are reinforced with elastic fibers that can stretch to several times their resting length and then snap back to original size. This gives the throat both the flexibility to expand massively and the structural integrity to not tear apart under the stress of holding 40 tons of water. And here's where it gets really impressive. The whale has to do all of this while moving forward. Because if it stops, if it just hangs in the water with its mouth full, it will sink. That much water weighs enough to overcome the whale's natural buoyancy, so the whale keeps swimming, even with its mouth full. The tail continues to beat, powerful enough to propel the whale forward, even when it's essentially dragging a swimming pool's worth of water. This requires muscle power that borders on absurd. The tail muscles alone make up nearly a third of the whale's total body weight, and they have to generate enough thrust to overcome the drag of that expanded throat. Then comes the filtering process. The baleen plates are arranged in rows, hundreds of them, hanging down from the upper jaw like the teeth of a comb. But they're not rigid. They're flexible, able to bend and flex as water pressure pushes against them. The spacing between these plates is precise, wide enough to let water flow through quickly, but narrow enough to trap krill. And the fringes on each plate, those hair-like fibers, create an even finer filter, catching krill that might slip between the larger gaps. When the whale closes its mouth and pushes water out with its tongue, the pressure is enormous. Forcing 10,000 gallons through those baleen plates in less than a minute requires the tongue to act like a piston in a massive pump, generating hydraulic pressure that would crush most biological tissues. But the whale's tongue is reinforced with dense connective tissue and muscle fibers arranged in layers that can withstand that pressure without tearing. And it has to be, because the tongue is doing this dozens of times per hour during active feeding. This entire system, the expandable throat, the flexible jaw, the baleen filter, the powerful tongue, evolved specifically to let the blue whale exploit a food source that no other large animal can efficiently harvest. Krill exist in massive swarms, billions of individuals clustered together in areas where ocean currents concentrate nutrients. But they're individually tiny, too small for most predators to bother with. The blue whale found a way to harvest them anyway. By scaling up to a size where it could take in huge volumes of water and filter out the krill in bulk, it gained access to one of the most abundant food sources in the ocean. And that food source is what made the blue whale's massive size possible. Because getting this big creates biological problems that have nothing to do with feeding and everything to do with basic physics. The cube-square law is a fundamental constraint that limits how large animals can grow. It states that as an animal gets bigger, its volume and weight increase faster than its surface area and skeletal strength. If you double an animal's length, you increase its volume by 8 times and its weight by 8 times. But you only increase the cross-sectional area of its bones and muscles by 4 times. This means larger animals are proportionally weaker than smaller ones. Their bones have to support more weight relative to their strength. Their muscles have to move more mass relative to their power. This is why you can't just scale up an elephant to the size of a blue whale and expect it to function. The legs would snap under the weight. The heart couldn't pump blood against gravity. The bones would compress and fracture. Everything would fail. Land animals hit this limit around the size of the largest dinosaurs. Estimates suggest that sauropods like Argentinosaurus, which might have weighed 100 tons, were pushing close to the maximum size that a land animal can reach before structural failure becomes inevitable. But blue whales weigh over 200 tons, double the mass of the largest dinosaurs. How is this possible? The answer is water. By living in an environment that provides buoyancy, the blue whale eliminates the biggest problem facing large land animals. Its bones don't have to support its full weight. The water does that. This is why blue whales have bones that seem ridiculously delicate for an animal their size. The skeleton of a 100-foot blue whale looks fragile compared to an elephant skeleton, with thinner bones and more open, spongy internal structure. But it doesn't need to be stronger, because those bones aren't holding up 200 tons of weight against gravity. They're just providing structure and anchor points for muscles. But buoyancy alone doesn't solve all the problems, because the blue whale still has to move that massive body through water. And water is 800 times denser than air, creating drag forces that increase exponentially with size. The blue whale's solution is hydrodynamic perfection. The body is shaped like a teardrop, widest about a third of the way back from the head, then tapering smoothly to the tail. This shape minimizes turbulence and reduces drag more efficiently than almost any other design. The skin is smooth and flexible, able to ripple slightly as water flows over it. These micro-movements actually reduce drag by preventing the formation of large turbulent eddies that would slow the whale down. And the tail is a masterpiece of biological engineering. It's perfectly horizontal, unlike a fish tail which is vertical. This orientation gives the whale more efficient up and down thrust, which is important because whales have to surface regularly to breathe. The tail flukes can span 25 feet across, providing massive surface area to push against water. The muscles that power this tail are among the most powerful biological motors ever evolved. They have to be, because moving 200 tons through water at cruising speed, which for blue whales is around 12 miles per hour, requires constant application of enormous force. But here's the really remarkable part. Blue whales can sprint. When they need to, when they're being chased by orcas, or when they're competing with other whales, they can hit speeds over 30 miles per hour. That's a 200-ton animal accelerating to highway speeds in open ocean. The energy required for this is staggering. The whale is burning calories at a rate that would exhaust most animals in minutes. But blue whales can sustain these sprints for extended periods because their cardiovascular system is operating on a scale that makes normal mammal physiology look quaint. That 400-pound heart isn't just beating slowly when the whale is diving. It speeds up dramatically when the whale needs power. At the surface, after a deep dive, the heart rate can jump to 30 or even 40 beats per minute as the whale replenishes oxygen in its blood and muscles. Each beat moves 60 gallons of blood. In 1 minute at elevated heart rate, the whale's heart is pumping over 2,000 gallons. That's nearly constant circulation of the whale's entire blood volume, which is around 1,500 gallons in a large individual. This rapid circulation is necessary because blue whales are deep divers. They regularly descend to 1,000 feet or more, chasing krill concentrations that exist at depth. At these depths, the pressure is crushing, over 450 pounds per square inch, enough to compress the whale's lungs to a fraction of their surface volume. So the whale can't rely on breathing during a dive the way we do. Instead, it stores oxygen in two places that most mammals don't use as efficiently: the blood and the muscles. Blue whale blood has a much higher concentration of hemoglobin than human blood, allowing it to carry more oxygen per gallon. And the muscles are packed with myoglobin, a protein that stores oxygen directly in muscle tissue, turning the muscles themselves into oxygen reservoirs. When a blue whale dives, It's carrying enough stored oxygen to stay down for 30 minutes or more. The heart rate slows to conserve that oxygen. Blood flow is restricted to only essential organs, and the whale essentially shuts down everything except the brain, heart, and tail muscles. Then, when it surfaces, everything ramps back up. The heart rate spikes. Blood flow increases. The whale takes several deep breaths, each one moving thousands of gallons of air through lungs that are so large you could park a car inside them. This is cardiovascular engineering at a scale that doesn't exist anywhere else in nature, and it has to work perfectly, because a failure at this size is catastrophic. A blue whale washes up on a beach in Chile. It's dead, but its body is still intact. A 90-foot-long mass of flesh and blubber lying on the sand. Within 48 hours, the whale begins to swell. Gases from decomposition are building up inside the body cavity, trapped under layers of blubber that are so thick and tough that the gas can't escape normally. The pressure builds. The whale's body inflates like a grotesque balloon, the skin stretching tighter and tighter. And then, with no warning, the whale explodes. The blast sends chunks of blubber flying hundreds of feet. Internal organs are ejected with enough force to break windows in nearby buildings. The smell is so intense that people a mile away report feeling nauseous. The entire beach is covered in whale parts, some of them weighing hundreds of pounds, all of them decomposing in the sun. This is what happens when an animal this size dies on land. The same body that functions perfectly in water becomes a biological hazard on the beach because the structural systems that work in a buoyant environment fail catastrophically under the full force of gravity. The organs, which in life are supported by surrounding tissue and water pressure, collapse under their own weight. The blubber, which in water provides insulation and energy storage, becomes a liability on land, trapping heat and accelerating decomposition. The gases that would normally disperse in water build up in enclosed spaces and create pressures that the body can't handle. This is the fundamental problem with being as large as a blue whale. You become so specialized for your environment that you can't exist anywhere else. On land, a blue whale is just a massive pile of tissue that's failing under its own weight. In water, it's the most successful large animal evolution has ever produced. But even in water, being this large creates problems that go beyond just moving and breathing. Because an animal this big needs fuel. Massive amounts of fuel. And getting it requires consuming quantities of food that seem impossible. A blue whale needs to eat around 4 tons of krill per day during feeding season. 4 tons. That's 8,000 pounds of tiny crustaceans, each one weighing a fraction of an ounce, consumed in a single day. To get this much food, the whale has to find krill swarms, which only exist in certain parts of the ocean at certain times of year. Blue whales migrate thousands of miles following these swarms, traveling from polar feeding grounds where krill are abundant to tropical breeding grounds where they give birth. These migrations are among the longest of any mammal. Some blue whales travel over 10,000 miles round trip, crossing entire ocean basins, burning through fat reserves to fuel the journey. And here's the critical part. The whales don't eat during migration. They feed intensively during the summer months in polar waters, consuming as much as possible and storing it as blubber. Then they live off those reserves for months while they travel to breeding areas, give birth, and travel back. A blue whale can accumulate blubber layers over a foot thick during peak feeding. This blubber can account for 35 to 40% of the whale's total body weight in a well-fed individual. That's 80 tons of stored fat in the largest whales, enough energy to fuel months of activity without eating. But this creates a precarious balance. If the whale doesn't eat enough during feeding season, if krill populations are low, or if the whale gets sick or injured, it won't have enough reserves to survive the migration. It will starve, unable to reach feeding grounds again before its energy runs out. This is why climate change is so dangerous to blue whales. Krill populations depend on specific ocean conditions, particular temperatures and nutrient levels that exist in polar waters. When those conditions change, when the ocean warms or acidifies, krill populations can crash. And when krill crash, blue whales starve. Not immediately, not during a single season, but over years. As repeated breeding cycles with insufficient food accumulate, the population declines. This is the vulnerability of being the largest animal ever. You need so much food, and that food is so specific that any disruption to the ecosystem can threaten your survival. Blue whales can't just switch to eating something else. They're locked into krill by millions of years of evolution that optimize their entire body for filtering tiny prey from huge volumes of water. But in stable conditions, when krill are abundant and the ocean functions normally, being this large provides advantages that smaller animals can't match. A female blue whale is giving birth. The calf emerges tail first, a safety mechanism that prevents drowning during delivery. The moment it's fully born, the mother nudges it to the surface for its first breath. The calf is 23 feet long. It weighs over 6,000 pounds, and it's one of the fastest growing animals on Earth. For the first year of its life, this calf will drink over 50 gallons of milk per day. The milk itself is incredibly rich, nearly 50% fat compared to 4% in human milk. Each gallon contains thousands of calories, enough that the calf gains 200 pounds per day. Read that again. 200 pounds per day. In a single year, the calf will grow from 23 feet to over 50 feet long and gain 50 tons of weight. That's growth on a scale that doesn't exist anywhere else in the animal kingdom. This explosive growth is possible because of the mother's size. A blue whale mother can produce hundreds of gallons of milk per day without significant strain on her system. Her massive body stores enough energy and nutrients that she can fuel her own metabolism, migrate thousands of miles, and still provide everything her calf needs to double its size in months. But this also reveals the cost of being this large. That mother has to consume enormous amounts of krill to produce that milk. She has to dedicate years of her life to each calf, nursing it for 6 to 8 months before weaning. And she can only reproduce every 2 to 3 years, because her body needs time to recover the energy reserves that pregnancy and nursing depleted. This slow reproduction rate means blue whale populations grow slowly. Even in perfect conditions, with abundant food and no hunting pressure, a blue whale population takes decades to recover from significant losses. And they did suffer significant losses. During the 20th century, commercial whaling killed hundreds of thousands of blue whales. Ships with explosive harpoons and factory vessels that could process entire whales at sea hunted them so efficiently that the global population crashed from perhaps 350,000 individuals to fewer than 10,000. The whales were killed for their oil, rendered from that massive blubber layer. A single blue whale could produce over 100 barrels of oil, making them incredibly valuable and driving hunting to levels that nearly caused extinction. Whaling was banned in 1966, and blue whale populations have slowly recovered. Current estimates suggest around 25,000 individuals worldwide. But that's still only a fraction of historical numbers, and the recovery is slow because of that reproduction rate. Each female can only produce so many calves in her lifetime. Each calf takes years to reach maturity. The population can't just bounce back quickly the way smaller, faster breeding animals can. This is the cost of being the largest animal ever. Your biology is so extreme, so specialized, so demanding of resources that you become vulnerable to any disruption. You can't adapt quickly. You can't switch food sources. You can't reproduce fast enough to recover from catastrophic losses. But in an ocean that's functioning normally, in an environment with stable krill populations and minimal human interference, the blue whale is essentially unstoppable. Nothing hunts adult blue whales successfully. Orcas occasionally attack calves, but an adult blue whale is simply too large to kill. Even a coordinated orca pod can't inflict enough damage to bring down a 200-ton animal that can swim at 30 miles per hour when threatened. The blue whale exists at a scale where it has transcended normal predator-prey dynamics. It's not competing with other animals for food, because no other animal can filter krill as efficiently. It's not worried about predators because nothing is large enough or powerful enough to pose a real threat. It's operating in a category by itself, alone at the absolute upper limit of what biology can achieve. And that limit is real. Physics and biology combine to make it essentially impossible for any animal to grow significantly larger than a blue whale. The largest individuals, over 100 feet long and pushing 200 tons, are already dealing with cardiovascular strain that approaches critical levels. The heart is working at near maximum efficiency. The muscles are scaled to their limit. The feeding system is consuming prey at rates that are barely sustainable. Going larger would require proportionally more food, but the whale's mouth can only expand so far. It would require more oxygen, but the blood and muscles can only store so much. It would require more power from the tail, but the muscles are already some of the strongest biological tissues possible. This is why no animal has ever been larger than the blue whale. Not the largest dinosaurs, not giant prehistoric sharks, not ancient marine reptiles. The blue whale represents the absolute maximum size that an animal can reach before the fundamental laws of physics and biology make further growth impossible. The largest animal that has ever lived isn't just a record holder. It's the record, the upper limit. The final answer to how big an animal can possibly get. And the fact that it exists, that it evolved to exploit a specific food source in a specific environment using biological innovations that push every system to its extreme, is one of the most remarkable achievements in the history of life on Earth. A 200-ton animal with a heart the size of a car, swimming thousands of miles across oceans, filtering 4 tons of krill per day through baleen plates, diving to crushing depths, nursing calves that gain 200 pounds per day, living for over 80 years, and doing all of it with a body that would collapse under its own weight on land, but functions perfectly in water. This is the blue whale, the largest animal that has ever lived. Not just the largest now, but the largest ever, in over 500 million years of complex life. And understanding how it got this big, what it had to overcome, and why nothing has ever exceeded it, reveals something profound about the limits of biology itself. The blue whale is proof that life can achieve sizes we can barely comprehend. But it's also proof that those sizes have limits, boundaries defined by physics and chemistry that even evolution can't overcome. And the blue whale, at 200 tons and 100 feet long, is standing right at that boundary, the absolute maximum expression of what living matter can become.